Hello everyone, welcome back to the channel. This video is the second part of transient analysis of RL series circuits. In previous video, I had solved three problems of RL series circuits. If you haven't watched that video, please check the link in the description box before watching this video. This video is actually extension of that video only. I will solve three more problems over here. The first problem is in the network shown the switch is closed at t equal to 0. Find Vt for t greater than 0. Now the network has a current source, a resistance of 0.5 ohm. Here we have a switch, 1 ohm, then an inductor of 1 by 3 Henry, and between these two terminals voltage is Vt, and this switch is closed at t equal to 0. So question is to calculate the voltage Vt, which is actually voltage across the inductor terminals. So how can we find out Vt? We can find out Vt by using expression L di by dt, where I is the current through the inductor. So firstly, we need to obtain the expression of current through the inductor for t greater than 0. Then we can substitute that expression of current in this equation in order to find out the voltage across an inductor. So let's start. The expression for finding IT is I infinity plus I0 minus I infinity into e raised to a minus t by tau. Now we need the value of I infinity, that is steady state current after switching, I0 initial current through the inductor that we find from the before switching conditions, and time constant. That's why we have three steps. First one is calculation of I0, that is from before switching conditions. Now before switching, what we have, a 3 ampere source is connected with 1 by 2 ohm resistance while the switch is open. On this side we have resistance and we have inductor. Now this inductor and resistor, they are connected in parallel. We don't have any source over here. That's why the current through the inductor is actually 0, because we don't have any source. So current through the inductor is 0 initially. Next step is we have to calculate I infinity from after switching conditions. After switching, now the switch is closed. We have two resistances connected in parallel and they are in parallel with the inductor across which we have to find out the voltage. And here we need to find out I infinity. So when the steady state conditions are reached after switching, the inductor will behave as short circuit. So we will replace this inductor by short circuit. Now this 3 ampere current which is flowing over here, it has three different options. It can flow through 1 by 2 ohm resistance, 1 ohm resistance, or through the short circuit. Now current has property that it follows a minimum resistance path, which is a short circuit over here. So current through 1 by 2 ohm resistance is 0, through 1 ohm is 0, and whole 3 ampere current will flow through the inductor terminals. So I infinity is 3 ampere. What we can say that all the resistances which are connected in parallel with short circuit, that is the inductor terminals, they are actually getting shorted. So the current through the inductor terminals is actually 3 ampere. So now we have the answer of I infinity, we have the value of I 0 as well. Next step is we need to calculate time constant, that is tau, which is L by R equivalent. Now let's draw the circuit. The current source, it will be replaced by open circuit, 1 by 2 ohm resistance, 1 ohm resistance, and then here we have inductor terminals from where we need to calculate R equivalent. Now how 1 by 2 and 1 ohm are connected? Across the inductor terminals, these are connected in parallel. 1 by 2 is in parallel with 1, so it's 1 by 3 ohm. Now if we calculate tau, tau is L by R equivalent. L was 1 by 3. So 1 by 3, 1 by 3, it's 1 second. I of t, which is equal to I infinity 3 plus 0 minus 3 into e raised to power minus t by tau, or I of t is equals to 3 into 1 minus e raised to power minus t amperes. The question was that we need to find out the voltage across the inductor terminals, voltage Vt, which we can calculate by differentiating this current with respect to time and multiplying it with L. So L is 1 by 3 d by dt 3 1 minus e raised to power t. 1 by 3 into 3 minus e raised to power minus t into minus 1. So Vt is actually e raised to power minus t volts. So we don't need to find out the expression of voltage directly. We can easily solve it once we have the value of current through the inductor. For that we have the same formula which we had used earlier. Now second problem is, in the network a steady state is reached with switch K open. At t equal to 0, switch K is closed. Find I of t for t greater than 0. We have two voltage sources. Here the resistance is 30 ohm and a switch is K is placed over here. which is closed at t equal to 0, then 20 ohm 1 by 2 Henry. This is the current which we need to find out. We know the expression, the same expression which we had used earlier, I infinity plus I0 minus I infinity into e raised to minus t by tau. We need to find I0, I infinity and tau step by step. Let's start with finding I0, which we can find out from before switching conditions. Now before switching, what we have, the switch is open, 20-volt source in series with 10-volt source, 30 ohm resistance, 20 ohm resistance, and here we have inductor. Now what is given? That steady state condition have been reached. When steady state conditions are reached, at that time inductor behaves as short circuit. So we will replace the inductor by short circuit. And then we can calculate that what's the current through the inductor terminals, which is I0. Now I0 is, we can calculate it by applying KVL, or simply it's these two voltage sources, they are connected in series, so 30 divided by total resistance 30 plus 20, so it's 0.6 ampere. I0, very simple. Next step is we have to calculate I infinity, which we can calculate from after switching conditions. After switching, 20-volt source, 30 ohm resistance, and here we have switch which is now closed. 10 volt, 20 ohm, inductor. So 20 volt and 30 ohm, they are connected in series with the, sorry, in parallel with the short circuit. So they will actually get short circuited. So they will not be the part of circuit anymore. The inductor behaves as short circuit under steady state conditions. So we will replace it by short circuit. And then we will find out that what's the current through the inductor terminals. Now it's very simple series combination of 10 volt source and 20 ohm resistance. So I infinity is 10 by 20, which gives us the value of I infinity as 0.5 ampere. Next step is to calculate time constant, again from after switching conditions. After switching, we have only one voltage source and one resistance, 20 ohm resistance, voltage source replaced by short circuit. These are the inductor terminals. So R equivalent is 20 ohm, tau, which is L by R equivalent, is, the value of L was 1 by 2, 1 by 2 into 20, 1 by 40 seconds. So the expression for current, which is equal to I infinity. Now answer for I infinity is 0.5 plus I0 is 0.6 minus I infinity into e raised to minus t by tau, 0.5 plus 0.1 into e raised to minus 40 t amperes. This is the value of current through the inductor. Now let's move on to the last problem. The network of figure is under steady state with switch at position 1. At t equal to 0, switch is moved to position 2. Find it for t greater than 0. This is position 1, position 2, and here we have switch which is moved from position 1 to 2 at t equal to 0. The source is of 10 volts. I is the current through the inductor terminals. Again, same expression for current. It is equals to I infinity plus I0 minus I infinity into e raised to a minus t by tau. Let's find out I0, I infinity and tau one by one. I0 we find out from before switching conditions. Before switching means the switch is connected in position 1. Here we have inductor. Now since the circuit was in under steady state conditions, it means the inductor was behaving as short circuit. So let's replace the inductor by short circuit. Find out the current through the inductor, and that is actually I0. So I0 is simply 50 by 40, which is actually 1.25 ampere. Next is we need to find out I infinity from after switching conditions. After switching, the switch is moved from position 1 to 2. So now the 10 volt source is connected in series with 40 ohm resistor and the inductor. Again, at t equal to infinity, it means steady state. T equal to infinity steady state, inductor will behave as short circuit. Let's replace it by short circuit. Once the inductor is replaced by short circuit, then we can calculate the current through the inductor terminals. It's again simple series combination of a voltage source and a resistor 10 by 40, which is actually 0.25 ampere. Next step is we need to calculate time constant. Time constant from after switching conditions, position 1, position 2, 50 volt source replaced by short circuit, 10 volt source replaced by short circuit, 40 ohm resistance, and these are the inductor terminals. So the equivalent resistance between inductor terminals is actually only a single resistance of 40 ohm, tau, which is L by R equivalent. The value of L was 20 millihenry, 20 into 10 raised to minus 3 by 40. So it's 1 by 2 into 10 raised to minus 3 seconds. Let's substitute all these values in the expression of IT. I infinity 0.25 plus I0 1.25 minus I infinity into e raised to power minus t by tau. So IT is actually 0.25 plus e raised to power minus 2000 t amperes. I hope I had taken sufficient problems to show you that how to analyze the circuits for transition from one state to another state when inductor and resistor are connected in series. If you have any feedback for improvement of content on the channel, please do let me know that in the comment section. Also, if you find the channel content helpful, please consider subscribing the channel. Thanks for watching the video.